Okay, so we're not going to walk through the whole thing, but mean value theorem. So as long as the function's continuous and differentiable on the same interval, closed on the continuous, of course, and open on the differentiable. So when we say that there's some all this says, so the slope of the secant, or the average rate of change, that there's some place where the slope of the tangent line, the instantaneous rate of change, they're equal. So taking a look at for the first example, okay, read through it. Okay, first we got to see, does it meet the hypothesis? Does it meet the conditions? Is this polynomial, quadratic, continuous? Yes, of course, it's a polynomial. Is it differentiable? Polynomials are always differentiable on entire, from negative infinity to positive infinity. So that means that we can use the mean value theorem. So that means someplace that the average rate of change, that's why it's called the mean, is equal to the instantaneous rate of change, or the secant line has the same slope as the tangent line. Okay, where does that occur? And go on from there. Maybe you'll catch my arithmetic error. So let's take a look at the visual for this one. So here we go. Here's that parabola. As you can see, here are the 2 points, the line through that, the secant line. Now, instead of drawing different lines, I'm going to start off with, okay, let's look at all of these lines are parallel. Same slope to the secant line, but somewhere down here, back it up a little bit right there, that's a tangent line. So there's some place where that instantaneous rate of change is equal to the average rate of change. So that slope of that tangent line is equal to the slope of the secant line. We can also drag the tangent around to get it to match, but I think this way you see it a little better about where the parallels, where we finally have, here's a secant line, that a parallel line is tangent, or yeah, line parallel to the secant is tangent to the curve. So that's all we're trying to do with this one, is do that. So in the second example, same thing. Is that rational function continuous and differentiable on the interval? Well, as long as you're, for rational function, if you're in the domain, it's continuous and differentiable. And yeah, if you're looking at, by the way, what's the excluded value? Not in the interval, so we're okay. And so we can be applied. So meaning, if we can apply it, that means that someplace the derivative has a value where the derivative between 0 and 3, got to say that, in that open interval, equal to that average rate of change, or negative 1/10. Did it again. I didn't do that. There we go. How about third one? Same function, change the interval a little bit, negative 3 to 3. Oh, wait a minute. The excluded value of x equal negative 2 is in the interval. Function's not continuous. Forget it. We're done. Don't even go any further. There may be one, but we can't guarantee anything. So we just say it doesn't apply and move on. Okay. I know you can read through that. So let's get the gist of this. You're driving, or Leadfoot's driving. The time and the driving is continuous. Okay, so that function of the speed against time, or speed in terms of time, is continuous and differentiable. You're not going to have any real sharp corners. You're not going to go from 30 miles an hour immediately, instantaneous, down to 10. Not going to happen. So we can use the MVP. So what is lead's average rate of change? Average speed. Well, about 82.286 miles an hour. So that's what the MVT says. Somewhere in that 35 minutes, he does Leadfoot is driving at that speed. That's all we can guarantee. Well, if that's over 5 miles over the 75 miles an hour, and get a ticket. By the way, word has it that the Indiana toll road does this. Like if you go out towards Notre Dame or Purdue, you better watch out. Kind of thing. Not Illinois. Illinois, they don't know that. But again, what's the average rate of change? We're guaranteed. Now, did lead go faster than that? Yeah. Slower? I would say probably on both of those. It all depends because of this physical situation. Lead's not going to get on the tollway at 82 miles an hour and get off at 82 miles an hour. We're going to be like maybe 40 going on and 40 getting off. So they got to catch it up somewhere. Going to go over it. But all they can guarantee is 82.286. Okay? And then the same thing as we go along here. Continuous and differentiable. Got another polynomial. So this time the rate of change is average rate of change 0. Okay, and so there's some C in that interval, someplace between 1 and 8, where the derivative is equal to 0. So, well, there's your average rate of change, and oh wait, that's because your endpoints on the closed interval are equal. So g of 1 and g of 8 are equal. Well, guess what? Somebody says, hey, guess what? That's going to always work since it is a special case of the mean value theorem, and gets a theorem named after him, Rolle's theorem. Notice the same start. Functions continuous on the closed interval a to b, differentiable on the open. But this other thing here, that the two endpoints have to have equal function values. If that's the case, then guaranteed we have a someplace in that interval there's a C where the derivative is equal to 0. Tangent line's horizontal. We've done a whole bunch of those. And the rest of these are the same. So first, is the function continuous and differentiable? Yep. Sign all trig functions on their domain are. Then, one additional check in terms of Rolle's theorem. So what's f of pi over 4? What's f of 3 pi over 4? They have to be equal. Then you can say that. So somewhere between pi over 4 and 3 pi over 4, the f prime is equal to 0. Now, if we were looking for that c value, we would find f prime, set it equal to 0. And the same thing, and then 7. Real quick. Okay. H is continuous because if we would take the limit from the left and from the right of 0, we would both get -6. And the function value is -6, so that would be okay. But h of x isn't differentiable because if we look at h prime of x, derivative of 6x squared minus 6, derivative of x squared plus x minus 6 is down here. Now, the derivative isn't continuous. So from the left and from the right of 0, we have two different values. So the derivative doesn't exist there. Remember, it's a limit. The derivative is a limit. So since that doesn't exist, h isn't differentiable, we're done. No matter what about h of -1 and h of -2. Doesn't matter. We just can't say anything because of that. Okay? So that's what that. Rolle's theorem helps us with other things, but it really doesn't help us with big pieces. The mean value theorem is really the big piece out of that.